So our next speaker is Iñigo Artundo from VLC Photonics, and he will be presenting Fabless operation in Photonic Integration.
Okay. So first of all, thank you all for coming, and I'm going to be the last presenter of today, so I'll try to make it short. So this talk is about an overview of photonic integration technology, but not only that, but also the ecosystem nowadays of fabless companies providing all kinds of services in this area. So for some of you, maybe it's redundant, but I guess it's helpful for all of the others that is working on maybe separate areas of photonic integration. And this tries to give a coherent view of all of the field and also all the trends. So the outline of my talk will be, first of all, a brief introduction about VLC and photonic integration technology. Then I will comment on what has been the evolution of photonic integration in the last years and also comparing it with electronic integration. And also I'll give a little bit of an overview on the different generic platforms that are nowadays mostly in Europe. And finally, I will give some market trends and takeaways. But first of all, a quick introduction about VLC. We are from Valencia, that's VLC about. It's not very low cost. Photonic integration is all about integrating an optical system into a chip, and that's what we do. We provide services in this area. We try to help people integrate their optical systems into a chip. We have been working as a spin-off of Technical University of Valencia since 2011. And, well, we are based in Valencia, although one of our founding members is in the Netherlands. We are now 7 people. The team is growing lately, and, well, we have a lot of background from our academic years. We have been working on this technology for more than 10 years here. So what is photonic integration? Well, as I said, it's exactly that. It's integrating an optical system into a photonic circuit or photonic chip. The advantages are exactly like in electronic integration. So first of all, obviously, miniaturization of the system, which is interesting for some applications or markets where the weight or the size of the system is important, like aerospace or avionics or things like that. Also, it's a simpler assembly because it's only one chip that you need to, let's say, package or assembly on your component. If you compare it with traditional assemblies of discrete optical components, this is much easier. And this also gives you a much more reliable approach. Obviously, like in electronics, you can scale up production to very high volumes, and also this gives you an advantage in cost. But one of the most important advantages is actually that you can scale up the complexity of the systems that you are integrating. So you can think of optical architectures that can integrate, I don't know, 100 different lasers or 100 modulators, and this gives you, well, freedom to think of architectures that wouldn't be possible up to now. And now this is being used in many different markets, mostly telecommunications and data communications, but also, as we have seen just now with Luthwave Labs presentation, also to microwave and terahertz, to sensing also we have seen many talks about that, also instrumentation and quantum optics, like we have seen also with ICFO. So no matter what's the end application, eventually all optical systems are integrated in the same way. So starting with a system concept, the first step is to define what is the optical architecture of this system. So choosing a material technology. We have seen that there are different material technologies nowadays. You have silicon photonics, you have indium phosphide, silicon nitride, silica. Each of them has different advantages and disadvantages. So it's critical to select what is the most appropriate one, and then translate these functionalities into specific devices that implement these functionalities into this material platform. Once this is clear, then we define the chip architecture, which is translating these devices into the material platform, let's say the building blocks, that you can later on assembly into a chip design, a layout. This is the circuit that we have. This layout is adapted for fabrication at different foundries. There are manufacturing foundries all over the world, mostly in Europe, I have to recognize, and each of them has different, let's say, characteristics, design manuals, design rule checks, that you need to adapt to. After manufacturing, you receive the dies, the bare dies from the foundry. These need to be tested. for optical and electrical characteristics, and eventually this needs to be packaged into a metallic or plastic encasing with electrical and optical connections like fibers, etc. Well, up to now, this has been made, let's say, in the optical component market or field in a vertical way. So it was only one single company that was producing, for example, lasers or modulators, and it was all integrated in a vertical way. They were designing the component, fabricating it, packaging it, testing it, which gives a very high-performance device, but you require a very high investment as well. As a contrast, you have the horizontal business model where you have, let's say, all these tasks can be outsourced to different partners. This is what is known as the Fabless model, which eventually gives you also a performing device, but at a very low cost, or let's say at a very low investment rate. This approach has been proven very successful in the electronics field. Nowadays, the revenue from fabless companies in the electronic field or the electronic market is almost 1/3 of the global revenues, and we are trying to push this model into photonic integration. So at VLC Photonics, what we do, we try to help or provide services in all these areas, and for the packaging and for the manufacturing, we are a fabless company, so we rely on external partners who perform these activities. So where are we now in photonic integration? Well, if we compare it with electronic integration, that has been following the Moore's law, probably you all know about that, but it's duplicating the number of transistors in a circuit. From the early 60s, we have seen that the number of transistors in a chip has exponentially increased, reaching thousands of millions nowadays. Well, the history of photonic integration is not that successful. It all started by end of the 60s, beginning of the 70s, with the first proposal for a photonic integrated circuit. And eventually, the first integrated components came up in the market around the 80s. I'm talking about lasers, photodetectors, modulators, etc. Eventually, there was one technology that started to put several components into a circuit, not only one single component, but systems, and that was PLC. Is the acronym of planar light wave circuits. It's mostly silica, glass. That was a technology that was very much mature in the late 90s until the telecom bubble. And in that moment, well, most of the photonic integration developments came to a stop, and a lot of investment was lost in the telecom bubble. But some other companies kept on investing in this technology, and soon there was a lot of investment also on research and development in Europe, and soon some companies started to launch into the market different products based on photonic integration. For example, there is a very successful case of Infinera in the States. They released by 2004 the first transceiver for transport networks, reaching 100 gigabits per second. And since then, many other companies have launched products in this market, like Luxtera with the first active optical cable in 2007 based on silicon photonics. Other different companies using different technologies, like, for example, Technovis working on the fiber sensing area with a fiber back-rating interrogator in indium phosphide. Medlumix, a Spanish company from Madrid, doing an optical coherence tomography on a chip using silicon photonics. Or Xi of Photonics doing a beam combiner for visible wavelength range using silicon nitride. The most recent announcement in this area has been Intel, that last year they announced that they launched their first transceiver product using silicon photonics, which has been a huge splash in the field because a company the size of Intel investing on this technology makes a lot of headlines, as you can imagine. So where are we now? Well, if we compare it with the evolution of electronics, it's obvious that nowadays the most complex photonic circuits nowadays have around, well, 1,000 to 2,000, let's say, components or building blocks in a chip. So we could say that we are still 30 years behind. And this applies to many things, not only the manufacturing, but also the design, the software, the packaging, etc. So why we are here? Well, there are three main differences. Because actually, if you follow the trend, if you compare it Moore's law to the evolution that we have had in photonic integration, they are very similar. I mean, the trend is almost exactly the same, although, you know, a few years in the past. And there are three reasons for that. The first one is, obviously, we cannot compare to digital electronics. In digital electronics, you only have one component, which is the transistor. In photonics, it's more similar to analog electronics. We have many different building blocks. We have lasers, photodetectors, modulators, and each of them requires a specific optimization, while in electronics you only optimize one component. Well, there is also a lack of applications that require, for example, the kind of complexity or the huge volumes or the target prices that we have in electronics. And also, well, there is a limit in the feature size reduction on photonics. We are limited by the wavelength of operation. So this is where we are now. There are different generic platforms. By generic, I mean that it's accessible to everyone and it's a stable process that everyone can access. And it all started in Europe around 2004, 2008 with the EPICSnet network of excellence, which gave birth to two separate platforms. The first one was based on silicon photonics, and the second one was based on indium phosphide. What we did in that time was actually to set the basis or the foundations for the platforms that were generic, in the sense that they were not adapted to any specific component or application field, but they were generic for whatever application. And they were also including a PDK, a process design kit, like we have seen this morning also with Phoenix software, that allowed external designers to have access to these platforms and design for them in a very easy and straightforward way. Also, this gave the idea to translate the multi-project wafer runs that we had in electronics to photonics. This is a way to share the wafer space among different users, so each of them has a space on the wafer, so you lower the cost of fabrication, and also you share the risk as well. So different platforms had different evolutions. Both platforms were supported by different projects along the years, giving birth to different ecosystems, and also on the way silicon nitride technology evolved as well, in the shape of either silicon nitride or triplex, which is, let's say, a branded type of silicon nitride. Nowadays, the European Union is betting very strongly on this technology, not only in photonics in general, but on integrated optics with different pilot lines addressing this. We have seen that in MIRFAB or PIXAP presentations, and also I will comment a little bit on PIX for Life as well. In the United States, there were also similar initiatives a bit later in 2011 by OPSIS, which disappeared, and Obama recently launched the AIM Photonics initiative last year, which is more than $600 million on establishing this kind of generic photonic integration platforms in the United States. So for silicon photonics, nowadays, all the foundries, the European foundries, are gathered through the common platform of EPICSFAB. There are different brokers like CMP or Europractice for this, and this is gathering 4 different foundries: IHP in Germany, IMEC in Belgium, or CEALETI in France, all working on what we call thin silicon on insulator, so that's 220 nanometers thick silicon. And there is VTT in Finland with what we call thick silicon insulator, so 3 to 4 micrometers thick silicon. On the indium phosphide side, there is the JEPIX ecosystem, which is a broker for 3 different foundries: the Fraunhofer Heinrich Hertz Institute in Berlin, the Smart Photonics in the Netherlands, and also Lyonics, also in the Netherlands, but not in indium phosphide, but in triplex, in silicon nitride. There are other foundries who are organizing multi-project wafer runs, like, for example, the Institute of Microelectronics in Singapore, and also CMC over the platform of the Institute of Microelectronics on silicon photonics. We also have CNM here in Spain. We have seen the presentation this morning, and also Ligentech in Switzerland doing the very thick silicon nitride. And recently, GCS, through the technology provider Intelligent, doing a special platform of indium phosphide, which is regrowth-free. But there are also many other fabs in the field that are not generic, but custom, so people can access these foundries for product development or process development, e-beam providers, and more other MPW runs coming in the next years. So a little bit more about PIX for Life. So PIX for Life is a pilot line that is set by the European Commission starting last year. And the idea was to develop silicon nitride technology to push the integration of life sciences and biophotonic applications. Here, the idea is to use silicon nitride because it's transparent from 400 nanometers up to, well, the infrared, and it's actually very low cost as well, which is very useful for mass-scale biophotonic applications. The idea is to have the same ecosystem starting from, let's say, engineering, design, fabrication, packaging, and testing under the same roof, the Pix4Line platform. This year, they will be starting to have MPW runs open to everyone. So if you are interested, you can also apply through the website using let's say the manufacturing platforms of IMEC in Belgium and Lyonix in the Netherlands. And mostly targeting, well, as I said, life sciences like multispectral sources, biosensors, OCT, cytometry, well, many others. Well, regarding, I've been focusing mostly on manufacturing, but we have to acknowledge that nowadays one of the main blocks in the road of photonic integration is characterization and packaging. It actually comes to more than 60% of the cost of developing a product or a prototype, and this is mostly to the fiber alignment, which has very strict tolerances if you compare it with electronics, for example, which is mostly done through the side of the chip using inverted tapers or spot size converters, or vertically using grating couplers, mostly done in silicon photonics. So things to consider here to lower the cost is to, well, to always try to stick to available standards in packages and templates for the software, like also Phoenix provided this morning. Try to always focus at the design stage on what is going to be the outcome at the manufacturing and the packaging to adapt the design to the requirements. And also consider very carefully what are the differences between packages, depending on the end application. So a few words about different market trends and some takeaways for you in case you are interested into getting into this ecosystem. The investment trend is clear. I mean, we see it all over Europe and also globally. There is a lot of money being poured into the field, into photonic integration, not only on pure research, which is a phase that has been already, let's say, overpassed, but also on the industrialization of photonic integration. Not only that, but also we see that from the market perspective, we see that there are many markets, starting with telecom and datacom, but being closely followed by sensors or instrumentation and biophotonics, where we see a lot of investment from private companies. And, well, more specifically on silicon photonics, where we see the biggest market, the trend is quickly catching up. As a conclusion and takeaway, I want you to focus on a few things. So this fabless ecosystem that I mentioned and I've been presenting on photonic integration is quite mature. So there are companies developing products based on that and coming into the market already. But this is still quite complex and is evolving very quickly. So it's, there is a clear proof that early adopters are having an advantage into the market, but still it's quite difficult to get into this market. So it's always good to learn before you get into the let's say, into the technology, and also to be ready to invest and insourcing only the core activities. A few things that we see from our side, we see that all these MPW runs are starting to get really mature, speeding up delivery and also having more runs per year. More foundries are starting to open these MPW runs. We see hybrid integration quickly catching up. Up to now, it was mostly, a topic of research, but we now see that there are serious industrial approaches towards that, and also silicon nitride catching up a lot of momentum. We see also in the software side the emergence of modules, design modules, and also some IP developments like in electronics. And obviously a lot of effort being poured into the standardization of packages, which is fundamental if we want to get into the market successfully. So this is all what I wanted to say. Thank you for your attention, and if you have any questions, please let me know.
Thank you very much for this nice talk. Do you have any questions then? Yeah.
Are you involved in any photonic standardization activity?
Oh,
Is this also important?
Yes, not really. I mean, standardization is mostly being done at the specification side on the application, for example, in telecom transceivers or datacom transceivers, and also on the packaging side, which is not our core activity. But we are very close to Phoenix, which are working on the initiative is called PDA Flow, which is trying to standardize different softwares to interact together, from simulation to design, modeling, layout, etc. And, well, there are some standards being developed in this area, so we are very close to that.
What are, from your point of view, the next steps that photonic integration community in Spain should make? Which are these next steps, from your point of view, in your opinion?
That's a good question. First of all is getting to know each other, which I think this week is helping a lot. Secondly is trying to guess what are the niches, the applications where photonic integration has sense in being used. Because photonic integration obviously is not for everything. There are some applications that has sense to integrate, others not so much. So this is important to identify what are these niches. And then, well, join together and start working on different projects.
More questions? Okay, I have one. Well, for example, when a customer knocks on your doors, does he know exactly which technology to be used? Can you advise him on which technology you'll be using for the project or for the specific product he wants? Or, I don't know, do you have any...
Well, depends. Depends very much on the, let's say, on the customer or the end user. Some people already know the technology, so they clearly know what they want, so they are aware of, I don't know, the advantages of silicon photonics, like you mentioned, the cost and things like that. So they clearly want silicon photonics and they know the foundry and they just want a design for that or a product for that. While some others is people that has a lot of experience or expertise on optics or photonics, but they don't have so much idea on integration. So the first step is to assess, well, the different technologies, evaluate the different trade-offs, the advantages and disadvantages. So it's very, very different, depending on the end customer or the end user.
Okay, so do you have customers that want a black box, for instance?
We have had
input, output, and that's what I want. I don't care about the technology, for instance.
We have had everything.
Okay.
From people that have no clue about photonic integration to people that really have, you know, everything specified and really have clear objectives.
Okay.
So, yeah.
Thank you.
That's actually one of the problems, that we see a lot of, let's say, miseducation on the field. Even in the photonics field, some people don't even know that their systems can be integrated. So sometimes it's difficult to get into meaningful conversations if they don't even know the technology itself. So there's a lot of work on that as well.
Yeah, I guess so. Okay, more questions? No? So let's thank the speaker again.
Thanks.
So I think that's the end of the session.
Yes, thank you, Antoine, for chairing the session, and thanks all speaker and all attendees today. So that is the end of the second day of Photonic Integration Week. We had planned to finish earlier today because we believe we are in a nice sunny city, but suddenly it seems like it was snowing during lunch. So there was nothing planned for, nothing officially or strictly planned for tonight. But as yesterday, if you want to informally gather each other with us, we will be happy to find somewhere to dine with you. So everyone interested in making some social thing, maybe you can stay here or approach and we discuss what to do. If there is nothing else, tomorrow we will be starting at 9:30, I think. Tomorrow we will have these 4 lectures more oriented toward learning the things that you can do and that you don't have to do when designing photonic chips for telecom and biosensing. That will be tomorrow morning. Okay? Thank you all again.